Hi to all, and thank you, Mariano, for the introduction. Uh, as we saw earlier from the keynote, my presentation will slightly deviate from the two previous ones, and I will try to introduce you very briefly, of course, in the second axis around which our project revolves, and that is the concept of hydroecological modeling and forecasting. To this objective, Prime Water introduces what we refer here to as a multi-model chain for hydroecological forecasting. In very few words, this concept uh, actually is a series of individual, let's call them submodels, that are linked to each other in an input-output rationale. This means that starting from the more upstream model, the outputs of which form part of the input to the more downstream and so on. So in our case, this link, this chain, this modeling chain comprises first the modeling of what happens at the upstream catchments um, of lakes and reservoirs. That means we're trying to predict river discharges, nutrient and sediment influxes, and so on. Moving downward, we simulate what happens inside the lake, from the circulation patterns to water quality variables that are related to phytoplankton blooms, and not only to that. And lastly, the outputs of these forecasting modules, let's say, from this series of model, can be furthermore linked to a multitude of potential downstream applications. Some examples of which I delineate here with the gray shades. For example, let's say some decision support tools for water resources management, or predictive maintenance tools for hydropower industries. There's a whole bunch of potential applications that can be linked with a more upstream uh, simulated forecasts. Now, within Prime Water, and in this presentation, we are going to be focusing in the three more upstream links of this modeling chain. And in this regard, we're working with two distinctive families of models. First, on one hand, we refer to the so-called process-based or mechanistic models, and on the other hand, we work also with data-oriented or empirical models. The process-based models, which in our case refer to both at the catchment level, the hydrological component, and the inland modeling components, are mostly an effort to mathematically describe some prior assumptions of what drives its system. On the other hand, the data-oriented solutions that we're working with, and which refer solely to water quality in this project, do not rely on such prior assumptions, but they are mostly trying to create functions that connect, that map specific inputs to outputs. But we will be reviewing all this into more detail in the next slides. Now, the major interest of our work is to investigate how we're actually connected with the two previous presentations, is how we can to investigate how Earth observation data can enhance hydroecological modeling and forecasting. And we have, let's say, clearly defined two distinctive families of experiments, of experimental investigations, that are clearly linked to the two previous modeling types. To become more specific, in terms of the process-based modeling part, what we're actually trying to investigate here is how to improve the forecasting capabilities of such models by assimilating Earth observation data. In other words, what we want to do here is to make use of the existing EO data in plain words, to bring our models closer to the extent possible to the real conditions, to reality. The second family of experimental investigations, which is dedicated to data-driven algorithms, aims to assess our potential to develop data-driven algorithms for the forecasting of phytoplankton blooms in lakes and reservoirs. Now, beginning from the process-based and the data simulation component of this project, if we want to summarize our primary, not the only, but the primary investigations that we're undertaking, the answer would be twofold. On one hand, we really want to assess to which extent the assimilation of EO-derived information can improve our forecasting capabilities, which is not self-evident. And at the same time, what we really want to do is to also evaluate how long the impact of these data simulation approaches will be. So naturally, since we are speaking about different modeling components, the assimilated data are going to be, of course, diverse. And by that, I mean that, for example, for the stream flow forecasting, we are referring, for example, to evapotranspiration products or snow cover related products, whereas for the more, for the inland, let's say, component of the modeling chain, we refer to chlorophyll A, surface temperature, and so on. Now, given the time restrictions, we have selected some very key findings from each of these modeling investigations. Now, starting from the hydrological component, we can now say that the assimilation of EO datasets can generally improve the initial hydrological conditions and hence the forecasts at short lead times, up to, let's say, 1 to 2 weeks ahead. Is this improvement uniform across all variables and seasons? The answer is no, it actually depends. For example, we've seen that snow water equivalents appear to be more influential, especially during spring, which is actually important to predict accurately spring floods. Lastly, and perhaps equally importantly, our work has indicated, and this highlights the relevance of EO data simulation, the fact that data simulation appears to have higher impact in terms of forecasting skills than the meteorological forcings, the accuracy of the meteorological forcings that we are using. Likewise, and this is a case study that we already seen, we're talking about the Mulargia reservoir in Sardinia. If we wanted to improve our ability to forecast phytoplankton blooms timely, our results indicate that we should directly opt for assimilating chlorophyll A products rather than using some indirect products, for example, temperature, which could potentially influence, but it appears that it does not impact chlorophyll A predictions. The assimilation of chlorophyll A showed not only improvements in terms of an average error reduction, which is also important, but I think more importantly, it safeguarded against extreme errors, which is also critical when it comes to decision making. How long this impact is in the forecasting skills, it seems that the model will come to its previous to prior assimilation to pre-assimilation trajectory within 4 to 5 days. So after these 5 days, the impact of assimilation dissipates. Now, very quickly, I'm stepping to the next families of experiments, which is the data, which is related with to the data-oriented approaches. So the major question here is if we can leverage the existing EO-derived water quality to develop credible models for phytoplankton, for predicting accurately phytoplankton dynamics. Now, why are relevant? Why are the EO-derived products relevant? I think for three reasons. First, they, especially multispectral, when it comes to multispectral sensors, they go quite back in time, and they can give us the ability to build large data sets. And this is a major obstacle that we can overcome, especially for data-oriented approaches. Second, they are available operationally, as for example, Karin showed in the first presentation. And again, quite importantly, they are pretty much available everywhere in the world. So the whole idea here, and this is what is illustrated from this graph at the bottom of the slide, is to train an algorithm that can connect, that can map hydrometeorological drivers in lakes and reservoirs to chlorophyll A values that are derived from multispectral sensors in various missions, Sentinel and Landsat and so on. So does this work? Which is actually the first question that we have to answer. The answer is yes, especially if we consider the graph on the left-hand side, and we compare the black circles with the red predictions. Errors are quite reasonable and acceptable. Naturally, there are some discrepancies, but overall, the algorithms developed appear to capture the variability of chlorophyll A variations, in this case study at least, without even producing large prediction intervals, without, let's put it in a few words, without offering highly uncertain predictions. Okay, the errors are acceptable, as we said, and they are low, but are they better than just keeping the last observation, which is a very reasonable assumption to make? Well, from our investigations, it appears that our approach, this forecasting approach, can be better than this last observation alternative for up to 10 days ahead. Of course, accuracy drops when we move from 5 days ahead predictions to 10 days ahead, but still, this is an approach that can give us more accurate predictions than just sticking to what we already observe and know. I do understand that it's too much information, so I wanted to just keep 3 very simple take-home messages. First, that the assimilation of EO-derived evapotranspiration and snow-cover products can improve sizably the forecasting capabilities of hydrological forecasting, especially during spring floods. Second, that the assimilation of EO-derived chlorophyll A into process-based models can enhance the forecasting abilities of ecological models of inland waters at least up to 4 days ahead. And third, the fact that EO-derived chlorophyll A can support the development of theory-guided, data-driven algorithms that can predict the appearance of phytoplankton blooms up to 10 days in advance. Naturally, this is only, as we said before, a small part, important, but not this does not cover all the experimental investigations that we are performing. So you are all more than welcome to visit our virtual lab and get a better look into other equally interesting findings and investigations that are related to the utility of Earth observation data into hydroecological modeling. Thank you all again for attending.